Hi everybody, and welcome to my paper presentation for CS6263. In this video, I'm going to present the Extended Technical Report, Peekaboo, a hub-based approach to enable transparency in data processing within smart homes. This was written by a number of professors at Carnegie Mellon University. Their names are here. I'm not going to bother trying to pronounce them because I know for a fact that I will butcher them. To be completely honest, I chose this paper primarily because of the name. It's not every single day you actually see a technical paper that is written on whose name is based upon a game that you play with an infant or a toddler. So based upon that was my criteria for choosing it. Probably not the best criteria, but heck, I decided to go with it anyways. This paper was originally presented at the 43rd IEEE Symposium on Security and Privacy in May of 2022, and you can find a video presentation of this paper by the authors, not just me, but by the authors at this particular website. In my presentation, I'm going to discuss the motivation behind Peekaboo, its design overview, primarily in software, but I'll also present the hardware that it was implemented on. I will then discuss their analysis of a variety of smart home scenarios, the programming approach for Peekaboo, which basically is a pipeline approach. I will present their evaluation of the work, which is more qualitative than is quantitative. And for those of you that are looking for a dissertation topic for your PhD, I have some ideas for you. This right here is an example of a smart home. Notice that this home has a number of smart devices, each of which computes to a cloud. And they do compute directly to the cloud. Now, it is true that many of them will go through a router, and then that router sends information and sends that data to the cloud, but the router is just a pipe. So the logical connection is pretty much from device to cloud. So there are many devices that transmits a whole lot of data, and those data types could be tabular data, it could be images, they could be audio, or they could be video. Once they get to the cloud, that is where the action happens. The cloud is pretty much the brains behind all of these devices. So the cloud provides a number of services. Basically, they process the data, they make decisions. Based upon those decisions, they send the appropriate commands to the devices, and of course, they will let you, the subscriber, know what's going on by providing reports whenever it is necessary. Big question is, what information are these devices sending to the cloud? It is quite sure, hopefully they are sending relevant information for the cloud to make decisions, or the very servers on the clouds to make decisions, but are they also sending information that, one, is not relevant, or two, may be sensitive or private? Are these devices basically compromising the privacy that you're supposed to enjoy at home? And the second question is, how can you verify or validate that only data necessary for cloud services is being delivered? We have a whole number of logical pathways. Most of them are primarily are independent, and it would be a very arduous task for somebody to verify that each of these links are actually sending relevant data, or more particularly, not sending sensitive data. For example, here we have, suppose you have a smart TV and your TV provider claims to send aggregate viewing data to the cloud on a weekly basis to help refine programming specific to your needs. The big question here is, how is that audited? How can you actually verify that the smart TV is not sending additional information, particularly sensitive information, like perhaps your social security number or your credit card information or whatever? Furthermore, there are other apps such as Hello Visitor and iLobby apps that identify visitors using faces and images. What happens is the camera will send that information to the cloud. The cloud, if you're using Hello Visitor or iLobby, the server at the cloud will perform their facial recognition. Well, the fact of the matter is, the only information that the server need, or that Hello Visitor or iLobby needs, are the faces. Doesn't need the car, doesn't need the wheelbarrow, doesn't need what I think is a trash can over there. So the question here is, how can we validate that really only the relevant information is being sent, or more importantly, how sensitive information may not be being sent. Well, there's a number of ways that you can do this. The first way is that you can actually increase the capability of your smart home devices to actually do this filtering. Of course, that would increase the computational load on those devices, which means that we require more powerful processors, and which would drive up their cost and complexity. The other way is to find some way to aggregate the data before sending it out. Of course, here, validation is still an issue. And then thirdly is we can actually leverage new mechanisms that are for trusted cloud computing, such as cryptonets or distributed machine learning. Unfortunately, these approaches have not yet matured, and they're challenging for users to verify and understand. Frankly, they're challenging for me to understand and or verify. So the author's approach is to put in a trusted hub inside your house. And this trusted hub is going to be a privacy-sensitive architecture for developers to build smart home apps. The idea behind this is that these apps will communicate with the hub. The hub will pre-process the data, removing irrelevant information, masking sensitive information, and then sending that pre-processed or refined data to the cloud for the process. Specifically, it will ensure that only necessary data is sent. It will minimize the transmission of sensitive information, and for sensitive information that must be sent, it will transform it in some way to actually maintain privacy. This could be through the blurring of images to hide sensitive information like a license plate number, or distorting the pitch of an audio clip to actually hide the voice fingerprint. Peekaboo's approach was based upon the analysis of over 200 smart home scenarios. These scenarios were drawn from the literature and also drawn by not necessarily design interviews, but more like brainstorming sessions conducted by the authors. And as a result, they came up with the following insights. The first one is that many cloud computing apps do not require raw data, but rather a subset of that data or a transformed version of that data. And the second is that a number of small operators can support many of these scenarios. And this is a consequence of the fact that there's only a finite number of data types that are used: tabular, audio, image, or video data. Peekaboo is implemented on a Raspberry Pi connected to a TPU accelerator. Most of the tasks, which are primary lightweight tasks, can be performed on the Raspberry Pi. There are a few computationally intensive tasks that require a TPU accelerator. The Raspberry Pi and the accelerator are programmed using a Node-RED visual programming environment, which was developed by IBM. You might notice that this looks hauntingly similar to the block-based programming that we actually used in our first project. Essentially, the operators that Peekaboo uses are programmed in JavaScript and are deployed into Node-RED as an environment, as a library, where each operator would be one of these little nodes that we can actually put onto here, and then connect using a pipeline fashion. Now we're going to move into our design overview. First, note that Peekaboo provides processing for all data before it's delivered to the internet. Peekaboo has basically three main components. One is the declaration of all pre-processing pipelines. Then it has a fixed set of chainable and reusable operators to specify that pipeline, to specify the pipelines. And then once they are specified, they are downloaded onto an in-home trusted hub that once again implements them and mediates access between all the smart home devices and the internet. As an example, here is our Hello Visitor application. Notice that the pre-processing pipeline can be identified as getting the image, detecting the face, cropping the face, and sending it to the cloud. The operators, which are implemented in software, would be the push operator, which is going to be pushed against the image, the detect operator, which would detect the faces, the crop operator, which would then crop the faces, and the post operator, which would then send that information to the cloud. Now, these are the nodes, or the nodes or blocks that you would actually pull out of Code-RED the Node-RED environment and chain together. And then once you've done that, Node-RED will then implement this onto your trusted home, in-home trusted hub. The design of Peekaboo considers the following threat model. First, we assume that the Peekaboo hub is trusted and uncompromised. Second, our model assumes that all Smote harm devices can only communicate to Peekaboo. There is no way that the devices can circumvent the hub and communicate to the cloud directly. Third, we assume that all Peekaboo operators are secure and do not have vulnerabilities. So everything here is trusted. The only vulnerability that exists in this contrived threat model is at the cloud. We assume that the cloud is not completely secure and may have vulnerabilities. So it is to ensure that, so it is necessary that all private information is either removed or masked before data goes to the cloud. A major part of the design and implementation of Peekaboo was the analysis of smart home scenarios. To analyze smart home scenarios, the authors evaluated over 200 smart home use cases. They were collected from a literature review of sensor-based scenarios for smart homes and also a review of mobile privacy research. They also had a brainstorming session with 7 participants, in addition to themselves, and those participants range from 21 to 60. What they did was they took all those use cases and they clustered them into 37 smart home scenarios. I have apps here. I probably should have said scenarios. The type of data each scenario requires is specified along with its constraints and the granularity of the outgoing data. And these scenarios are delineated in Table 7 of the paper and are also delineated in the appendix for this, the appendix of this PowerPoint presentation. And these were their results. The first one was that most cloud services do not require sensitive data. Most pre-processing functions share similar actions regardless of the data type. In other words, they are data agnostic or data independent. And thirdly, most of the processing functions are, 1, lightweight, don't require too much processing power, and non-proprietary. In other words, they are primarily open source. So how do we program Peekaboo? Well, primarily they use operators, and these operators use a pipe and filter software architecture. Basically, it's a pipelining process. And Peekaboo, the API provides 16 operators in 5 categories. And the first category, the provider category, basically is associated with getting data from the device. The inference category involves basically collecting or detecting and isolating features in that data. The filter category involves either removing unnecessary or sensitive information or hiding that information. And of course, the network category involves posting the refined data into the cloud. The utility category is primarily for debugging, or in some cases, if we have a more complex app, the join operator tends to be used. So here's an example of the inferring category, here where we actually infer content. Inferring content basically involves 3 operators. The first operator is the detect operator, where you detect an object in the data. The classify operator is where you classify not necessarily the dominant category of the data, but you classify the various categories in the data into certain classifications. And the extract operator is where you extract a certain feature of the data. In terms of filtering, the filtering category basically involves securing the privacy of the data, either through the removal or from masking. For example, in terms of masking, we may want to replace sensitive information with an artificial payload. We call that spoofing. Another way of hiding it is by injecting a small amount of noise or some sort of transformation to hide the identity of the data, for example, of hiding the voice footprint for speech. The select operation is where we actually select only the relevant data and disregard everything else. Aggregate is where we would just summarize, we would not send the data itself, just a summary. And then retrieved is where we might overwrite certain parts of the raw data with derived data. An example of changing of chaining operators into a pipeline is provided here. And here we are going to consider an incognito voiced assistant app that collects speech and hides the identity. And this app might be programmed using our operators as follows. The first operator would be a push. This is where we would sit there and we would wait for speech, for audio to be presented to us. Once the audio comes in, we will detect it for speech. If speech is detected, we will select it. And as all of you know, each of us has a different speech footprint, and we can mask that footprint by noisifying the data, either by adding noise or doing some sort of a pitch transformation. And that data, which still contains the relevant content, but not necessarily my speech footprint, would then be posted to the cloud. Next, we will talk about the evaluation of Peekaboo. Once again, Peekaboo, the evaluation is more qualitative. However, I do have a few quantitative results. The first evaluation was, well, out of the 68 smart home apps that they developed, how many of those apps require raw data and only raw data? And it turns out of the 68 apps, only 3 require raw data. One was a smart cooking device. The other one was a smart toilet that analyzes fecal matter for diseases. That is kind of gross. And the other one was a microphone that measures lung function. The other 65 apps took advantage of either context selection or conditional filtering, only sending relevant data, or explicit noise injection, basically to change the pitch of a speech recording to hide the identity of the speaker. Another thing they were concerned about was speed and latency, and this is primarily because the Peekaboo architecture has a hub that has limited computing resources, so it's not the fastest thing in the world, and we use a pipelined approach that introduces latency. So they conducted a number of experiments to quantify the computational load and the latency. This is a result of the amount of time required to execute certain tasks. And their primary result was that the Raspberry Pi and the TPU could support 25 inference tasks, such as these, and over 100 filtering tasks per second. And then the average latency, which is described qualitatively described in this graph, was comparable to that of cloud-based approaches. I can only assume that is the case because in the cloud-based approach, you also have to consider the latency required to get the app to the cloud so that it can actually process it. Another thing they wanted to evaluate was the ease of developing apps for Peekaboo. To do this, what they did was they found 6 developers. Each of these developers had 3 years experience in developing mobile apps. And they asked each participant to develop 4 applications. Those would be the 4 tasks. Before they developed the tasks, they were given an introduction to Peekaboo, introduction to the red nose interface, where the apps would be developed, a basic documentation on the operators, a collection of unit tests, and an example of what an app would look like, namely the Hello Visitor app. This table shows the amount of time it took each operator to complete their 4 tasks. And as you can see, each operator was able to complete all 4 tasks in less than an hour. I think we had one operator that could do it in less than 20 minutes. But nonetheless, the primary result that they report is that all participants successfully completed all tasks within an hour, and all participants found Peekaboo relatively easy to learn. Okay, so for those of you that might want to move on to do your doctorate, you might want to think about you might want to think about dissertation ideas. Well, here are a few. These are some future work ideas relative to Peekaboo. And the first one is the development of end-to-end encryption. As you can see, Peekaboo can provide two encrypted links. One is from device to hub, the other one is from hub to cloud. But if you want to make sure that your system is completely secure, you want to have encryption at both ends, not just at your separate links. So that would be an interesting research idea. Another area for future work is to develop more features for the hub. Basically, ways to aggregate installed manifests or installed apps, to find a way to develop more user control and data flows, and also to allow the user application of global filters. A third idea is to provide support for other communication patterns. Right now, Peekaboo provides apps for improving privacy from hub to cloud data flows only. As you've noticed, Peekaboo takes information from the devices and then sends data to the hubs. That's the only direction it goes. So a possible research direction would be to come up with an approach, a design that would support cloud to hub communication, or cloud to device communication, or an approach that would support device to device communication through the hub. And then finally, which is kind of unique to this particular class, is come up with an approach that provides information from the device to the hub to physical actuators. And then finally, a very important area of research would be unpredictable hub program rewriting. For basically, each of these apps can be easily rewritten, particularly maliciously. This could cause an adverse effect on the intended performance of the hub and apps, and also could cause potential damage. And so protections need to be researched to counter first, research needs to be conducted to identify these vulnerabilities and to develop countermeasures for these vulnerabilities. So the conclusions that are presented in this paper are as follows. First of all, Peekaboo is a new smart home development framework that uses an in-home hub-based approach. It helps developers build privacy-sensitive smart home applications, and it deploys these apps in an in-home user-controlled hub. The design of Peekaboo incorporates the following ideas: the performance of repetitive data processing tasks at a user-controlled hub, supporting the implementation of these tasks through chainable operators, and deploying pre-processing tasks in a pipeline that is comprised of these particular operators. As an appendix, I offer the summary of smart home scenarios that were actually used in the study. There are actually 37 of them, and they are discussed here. What you will see are their ID, the kind of tasks they're using, and the sensors that are used for each of these tasks. For example, here is the smart toy recognizing rear end, analyzing poop for diseases, and the relevant sensors would be the camera, and I guess the pressure sensor to determine when someone's actually sitting on the toilet. And that is all I have for this presentation, and I look forward to your questions. And with that, this is Bob Boyle, signing off.